I know more about CRP, and in the past few years, I was able to produce several papers in CRP as well. So I'm really happy to be here today. So about myself, okay, it's slightly different from all the presentations in the morning. I'm doing some kind of interdisciplinary research. So first half of my research is focusing on advanced manufacturing. So to be more specific, it's about additive manufacturing. I start with material extrusion additive manufacturing, gradually expand to DLP and, for example, metal processing methods. So the main idea is to produce some medical engineering implants. So this directly associates with the rest 50% of my research. It's about tissue engineering. So in this particular field, we have something called the tissue engineering triangle, basically describe the method for us to produce new tissues, to do the tissue engineering. There are scaffold-based approach, cell-based approach, and inducement-based approach. Where my research is mainly focusing on scaffold-based approach. That's exactly the place that additive manufacturing is driving the innovation in this place, in this particular point. So basically, my research is doing additive manufacturing, 3D printing, tissue engineering. That's it. So I think next I should introduce a little bit about the general concept of this research. Okay, I'm focusing on bone tissue engineering scaffold. Bone, as we all know, is one of the most important tissue in our human body. It gives support for the human body and also give protection to our organs and also generate growth. So similar to other type of tissues or organs, so when bone gets hurt or damaged, they have a certain capability to do the self-regeneration. Basically, it depends on the age or the gender. When the bone loss is between 5 millimeter to 15 millimeter, bone is able to do this self-regeneration without any clinical intervention. However, if it's beyond this scale, we call it critical size, so some clinical approach must be applied to join the bone to achieve the reunion. So conventionally, we have different methods, for example, using metal implants or different kind of biological grafts, autograft, allografts. They all present certain problems and limitations clinically. For example, stress shedding effect, ethical issues, the risk of rejection or transmission of diseases. So that's why, with the development of advanced manufacturing technology and with the development of advanced materials, researchers are able to produce synthetic, biocompatible, biodegradable bone tissue implants. And this is where material extrusion additive manufacturing start to step into this particular field. And then this is where my research starts. And then when I start this research, we try to adapt the concept of reverse engineering because we want to maximize the advantage of additive manufacturing, which is mass personalization. So different from other type of standardized engineering products. So bone defect and the scaffold, the field is bone defect, varies from patient to patient. It's possible for all the defects to be the same. So that's why imagine if we are able to use a reverse engineering method to 3D scan this defect, generate the data flow and feed it to the 3D printer. Correspondingly, we are print that scaffold that perfectly is the defect. So this is the ideal scenario. So that's why we start our research in this direction. And at beginning stage, we have noticed that the scaffold design, material, and fabrication procedures could all influence this product performance, which basically the better performance of this scaffold. So that's why, as engineers, we are trying to use engineering method to program, to manipulate this biological performance. And also, we can also go one step forward. We can using advanced manufacturing. We are using engineering method to solve more complex problems. Not only to do the bone generation, but for example, also can do the bone cancer treatment and post-treatment regeneration. So for example, using this type of support, multi-layered, multi-scale, multi-material to achieve a single function. Basically, we are providing a packaged solution to the clinicians. So this all starts with advanced manufacturing, additive manufacturing. So to here, a quick summary of the general context. So this research topic is start with additive manufacturing. I'm using additive manufacturing technology by design and manipulate or program different manufacturing variables in order to achieve a good scaffold performance. And we shouldn't say good, but what is good is it satisfies the user's need. Basically, it satisfies clinician's need and the patient's need. Okay. So in this way, in real world, what kind of research are we doing? So I'm trying to package this as design, fabrication, and evaluation. Okay. In terms of design, this is the first phase, basically scaffold design and fabrication. It's very standard mechanical engineering design and advanced manufacturing. But gradually we are introducing human-centered design and biomimetic. In terms of fabrication, we put in terms of characterization, we put characterization and optimization together because again, it's kind of standardized design and redesign procedure. In the end, we do the numerical biological characterization, basically test our product in animal bodies before we pass this product to the clinician. So next, I will using a couple of slides help you visualize our research. So lots of slides, I will go very fast, and the time is very limited. First stage is to do the scaffold design fabrication. Here I take a typical example. This is the standard design for a scaffold before we adopt the biomimetic elements. So 3D cubic porous structure, but again, it don't have to be this kind of cubic. They can shape according to the size of the bone defects. We are relying on through-assisted material extrusion additive manufacturing for the fabrication, matching different type of design, different materials. We are doing the process of optimization to get the optimal fabrication parameters. Into material, we are developing our own composite material based on some other materials developed by materials researchers. We are very close to our materials. Our base material, very importantly, is biocompatible, biodegradable polymeric materials because we don't want the surgical procedures to repeat multiple times. So it has to be biodegradable. And then in order to lift the performance of the scaffold to higher level, we are using carbon nanomaterials, for example, graphene to increase the mechanical strength, electrical conductivity. Graphene is very popular in countries. And also in terms of bioceramic, we are using piezoelectric ceramic to coupling the piezoelectric effect. Apart from the scaffold design, so my group also did a little bit about the we also do a little bit about the manufacturing system. Okay, we're still based on the standardized additive manufacturing technologies, but gradually we are trying to develop hybrid additive manufacturing system. Basically, bring additive manufacturing together with other advanced manufacturing technologies. In this scenario, electric spinning, and also I have some collaboration with some other colleagues sitting at the corner of this room doing the plasma surface treatment as well. The ultimate goal is to develop our unique system to fabricate a high-performance scaffold. Because before this, we don't have a particular additive manufacturing system fully dedicated to tissue engineering scaffold. So after fabrication really is a lot of characterization. So I try to summarize as this. First of all, morphological evaluation to evaluate the printed product close to our original design. Then I will move really fast. Chemical categorization, evaluate the exact chemical compound in this scaffold. Mechanical categorization to make sure the scaffold is able to withhold the mechanical strength of human load. Electrical conductivity measurement. For some scaffold, we want it to couple the electrical stimulation therapy, so we want it to be electrical conductive. Surface characterization, we characterize the surface elasticity, surface texturing, because it all influences the cell electrical behavior. Then gradually we move on to in vitro test. Basically means we're doing a test in the lab, in the bioplate with cells. So first of all, we do the initial degradation test. We must know the scaffold can stay in human body for a certain period of time, and it's functioning well. It's able to release certain biological molecules. Again, we're able to control these release through the manufacturing process using engineering methods. We have different correlation theories created. So next is the beauty of this research. When the cells get involved, we do the initial immunoresponse to test the scaffold don't get directly in the body, and then we do cell proliferation and diffusion. proliferation means it tests if the cells are able to grow, proliferate, expand very well in this engineering product in the scaffold. And differentiation means if the cells can successfully change from stem cells to bone cells, if this kind of product can really achieve its function, become bone. So, beautiful images. These are standard approach in this particular. So next is scaffold performance optimization. So this is the essence, and this is where my publication in CRP landed. So that we are using different engineering methods, advanced manufacturing methods to enhance its performance. For example, we are manipulating the functional field of the demographic by using such shortening the barrier to increase the barrier performance. We are also simply changing the scaffold surface properties in chemical testing, correspondingly increase barrier performance. Or more advanced approach of a system developed by another faculty member, we are able to in situ to do the cold plasma surface treatment during the 3D printing process. Again, changing the surface property that better barrier performance. Or another one using protein coating directly enhance barrier performance. Or drop cloth, another method also published in this journal. So in the end, we are able to produce this kind of result much better compared with the conventional, no matter medical implant or the biological grafts. So in the end, last step before we pass these samples to the clinicians, always need to perform in vivo biological characterization. The apologies for the next slide may be a little bit scary, some animals get involved. We are using an animal model to test our 3D printed samples. And then we are extending testing days to 30 days, 60 days, and 20 days. Just for your reference, a standardized large-scale bone regeneration process is around 180 days. So really, we are trying to accelerate this procedure. So we are able to achieve the fully bone regeneration in between 60 to 120 days, because 120 is already bone remodeling. And beyond that, we are also trying to investigate a little more, increase mechanism. Why this kind of engineering method we have applied is able to influence this biological performance. We're choosing different growth factors, different gene markers, we are doing some kind of analysis. So ultimately, it points out by selectively depositing different kind of advanced materials, taking graphene as an example, it can selectively enhance the mineralization at different bone regeneration stage according to our scaffold. Basically, is conformal to the shape of our scaffold. So here's comes to the conclusion. So this research justified is able to use material extrusion additive manufacturing for the fabrication of complex designs by mimetic, multi-scale, multifunctional bone tissue scaffold. Well, in terms of future, what is the future based on research? I would say one future, as I mentioned, would be the development of the biomanufacturing systems. Because after additive manufacturing, here comes the concept of bioprinting. So it's very important to have a kind of system dedicated for this particular application. Another one is to research a little bit into the principle of additive manufacturing. So we know additive manufacturing is kind of like a manufacturing process introduced to anisotropy. Material anisotropy would also influence the biological performance. We're able to manipulate the material. Anisotropy is also very important working on this. So in the end, thanks so much for this opportunity, and I'm open for any questions. More than welcome for any future collaboration. Thank you.
Thank you everyone for a very interesting talk. Any question from the audience, please?
Yeah.
Tom, yeah.
In your immunological assays, you looked at IL-1 beta and TNF alpha. Did you look at any like M2 associated cytokines?
So I think this is a very early stage of research. We didn't apply so many gene markers.
Okay.
Because at that time we are using the mouse cells. So I think we have planned to apply some human cells afterwards.
Sure.
And using a more broader spectrum of gene markers.
Okay.
Very good.
Nice. Thank you.
So by the way, the reason why we do so is because this test is done before we do the in vitro test before we do the predictive differentiation. That's why we do this so fast.
Sure. Okay.
So is that the in vivo test what you tried with the mouse cells then?
It's the immune test. So the idea is we're using the cells. There are two approaches. Either we apply stem cells, or we're using the cells from the animal body itself. For this test, we don't apply any actual cells. We put the scaffold. We're using electrostimulating therapy. Basically, is to speed up and promote the cell generation. So that's how we design structure as it is. It's acellular structure, no cells.
And what's the additive method that you use to produce these?
For this particular one, we are using, we begin with material extrusion additive manufacturing, and then
FDM based.
FDM, yes. And afterwards, we combine this with electricity.